Now let's get a little more statistical and scientific and talk about statistics we could store and how we could make them even better. So our estimation procedure right now has assumed that we only knew very simple things about our tables, like the number of distinct values, the number of tuples, the low value, and the high value. We can do better than this, and one common way to do better than this is to store histograms for each column. And so a histogram, as you may know, is an association of frequency, the number of records in our case, with a value. So we often in databases use what are called equi-width histograms, where each bin in the histogram is equally wide. So in this example, the table on the left corresponds to the picture on the right. We have values 0 to 0.99, 1 to 1.99, 2 to 2.99, and so on. And so the value domain has been evenly split. And the number of values per bin varies quite a bit. Some are 2, some are 3, some are 1, some are 8. Okay, and so you see this very spiky looking histogram, but all of the columns, so to speak, the vertical columns are equally wide. A different approach we could do is what's called an equi-depth histogram, where we try to make each bin equally deep, maybe off by 1 from each other. You can't always get everything exactly equal. And then the way you do that is by adjusting the range of the bin on the x-axis. So here's an example for the same data set. We're going to have one bin from 0 to 0.99, one bin from 1 to 1.99, one bin from 2 to 2.99, one bin from 3 to 4.05, and then one very tight bin from 4.06 to 4.67, and one even tighter bin from 4.68 to 4.99, followed by a very wide bin, 5 to 6.99. And the key is that each of these bins is between the range of 2 and 4. It's only off by 1 from 3. Okay, and so we say it's equi-depth. It's actually not exactly equi-depth. It's plus or minus 1 equi-depth. And the idea here is that in the equi-depth histogram, we've divided the data up into ranges of equal count. So these are 10 bins, so these are like deciles. Similarly, you would have quantiles if you had 4 bins. The median of a data set is the value that's halfway through an equi-depth histogram. Okay, and the cool thing about equi-depth histograms is that the frequent zones in your data get their own special bucket that measures them very carefully. So in the equi-width histogram, we had this big bin that went up to 8, and we didn't have any granularity about what was happening in that bin. In the equi-depth histogram, we get good granularity because we get finer partitioning within sort of that range of values. There's actually an even fancier histogram called a v-optimal histogram that tries to optimize this trade-off between what values go in what bins for selectivity estimation. So you should be aware of these things. You can read about v-optimal histograms on Wikipedia. We're going to work mostly with equi-width histograms in our discussion today because they're easy to do arithmetic with, essentially. But you can be aware of equi-depth and v-optimal histograms as good things to know. Having defined histograms and decided that we're going to work with equi-width histograms, let's get on with the task of computing selectivity using them. Assume in this case we have 100 rows and we have a selection predicate of the form select p greater than 99. We have the histogram down on the lower left, which defines p as the number of potatoes consumed per year. And we are able to see that for p greater than 99, it's the rightmost 4 bins that represent those tuples. And so we can count up the sizes of those bins and sum them. And so it's going to be approximately 50 values that fall in those bins. 50 out of 100 is 50%. So the selectivity of this predicate based on the histogram is 50%. Now let's look at another selection predicate, age less than 26. We have a histogram for this column as well, and the bins that are involved in this query are the lower left 4 bins, plus one of the values in the next bin over, between 25 and 30. And so we have to ask ourselves how many tuples fall into that little vertical blue slice of that bin. And here's where we're going to make an assumption. We're going to assume that the width of that slice is the same proportion as that proportion of the tuples. So it's the same as the height of that slice proportionally. So another way to say that is we're going to make a uniformity assumption. For every value in that bin, 25 to 30, 25, 26, 27, 28, and 29 will get an equal-sized number of tuples. That's a uniform distribution of tuples to values. And so we'll assume, therefore, that our 1/nth of the values is also 1/nth of the tuples, n here is 5, so 1/5 of the population of that bin, 25 through 30, has age less than 26. And so we take the full values of the leftmost bins, 10 plus 10 plus 15 plus 10, and then 1/5 of the height of the bin that we overlapped, which was 5. So 1/5 times 5 is 1. That's a total of 46% of the values in the entire histogram. So within a histogram bucket, we make uniformity assumptions, and of course the histogram itself gives us more detail across buckets. Now let's look at a more interesting scenario where we have a selection with a conjunction in it, the selection p greater than 99 and age is less than 26. In this case, we're going to make another assumption, which is that these two predicates are independent of each other. That is, the probability that you're a particular age is independent of the probability that you consume a certain amount of potatoes. Okay? So if you want to look at this on the left-hand side, we're going to take the potato histogram and we're going to shrink it proportionally by the estimates of the overlapping age bins. And so we'll see for potatoes 100 through 140, we're going to shrink each bin by 46% because we had 46 on the right-hand side. Alternatively, if you want to look at the age histogram, we could say that every age bin is going to be shrunk by 50% because of the potato consumption percentage. Either way you slice this, you're going to come up with 50% times 46% on the left or the right, which gives you 23% of the total values. And this assumes this independence of the two predicates, which won't always be true. It might be the case that old people like potatoes better than young people, but we're going to assume independence all the time in selectivity estimation. Having looked at conjunction, it's natural now to look at disjunction. Our same 100 rows, we have a selection p greater than 99 or p less than 60, which is reflected in the blue bars in our histogram. And you can imagine that the right thing to do here is simply to sum these together. We want to sum up the total number of bars, so in this case it's going to be a 53% selectivity. So disjunction seems pretty easy. But let's think about how it works across columns. Now we've got selection of p greater than 99 or age less than 26. Those are overlapping predicates. There might be some people who have more than 99 potatoes consumed per year, but they're young, they're less than 26, and we don't want to double count them. So every answer tuple is going to answer one predicate, 0 predicates, or 2 predicates. And so by the independence assumption, we can say there are some tuples that satisfy the first predicate, that's 50%, some that satisfy the second predicate, that's 46%, and then some that satisfy both, which by independence is 50% times 46%. So the selectivity is the sum of these first two values minus the overlap. So it's 50% plus 46% minus the ones that satisfy both, which is 50 times 46, for a sum total of 73%.